Okay, let's dive right into this explainer on Proximal Policy Optimization, or as we all know it, PPO. If you've been tracking the massive leaps in machine learning recently, you have absolutely interacted with a model trained using this exact algorithm. Today, we're going to unpack the mathematical blueprint that quite literally redefined how AI learns from trial and error.
To really understand the evolution of modern AI, we have to start with a kind of perplexing question. Why does a specific algorithm, introduced way back in 2017, remain the undisputed industry standard nearly a decade later? I mean, in a field where state-of-the-art models get replaced every few months, PPO has this unnatural staying power. And the answer? It lies in a brilliant, relentless compromise between theoretical perfection and raw, pragmatic engineering. Let's look at how it works.
We'll hit 5 key areas today, starting with the core problem with older policy gradients, then breaking down PPO's clipped surrogate solution, walking through the actual training loop, diagnosing some common pitfalls, and finally, looking at its massive real-world impact. All right, Section 1, the policy gradient problem, or what you might call the Goldilocks dilemma of early AI training.
Before PPO came along, training a reinforcement learning agent was a massive headache of extremes. You basically had to choose between algorithms that were either incredibly reckless with their data or paralyzingly slow to compute. On one side, you had A2C, Advantage Actor Critic. It's strictly on policy, meaning your gradient update needs data sampled from your exact current policy. You take one single update step, your policy changes, and boom, all the data you just collected is now off policy and completely useless. On the other end of the spectrum was TRPO. TRPO fixed the data problem by constraining the updates so the model wouldn't drastically overwrite itself. Safe? Yes. Theoretically clean? Absolutely. But it required a mathematically brutal conjugate gradient solve for every single update. You were basically doing complex calculus gymnastics just to take one step. Nobody runs TRPO anymore because the math is just miserable to compute.
To really visualize how wasteful A2C was, just think about the number 1024. In standard Atari environments, a single rollout across 8 parallel environments gives you exactly 1024 transitions. That takes roughly a dozen seconds of environment time to generate. Because A2C is on policy, every single one of those 1024 precious transitions gets thrown in the trash after just one gradient step. It's an astronomical waste of compute, making training agonizingly slow and incredibly expensive.
Which brings us right to Section 2, the clipped surrogate solution. PPO's just right fix.
So, to stop throwing away all that expensive compute power, PPO found a way to safely reuse data, and the bridge that makes this possible is called the importance ratio. It's actually pretty straightforward. It's simply the likelihood of the new policy taking a specific action divided by the likelihood of the old policy taking that same action. If that ratio is 1, it means 0 change between your new and old policy. If it's 2, your new policy is twice as likely to take that action. By tracking this single ratio, PPO always knows exactly how far it has drifted from the original data it's learning from. Now here is PPO's core mechanic, the clipped surrogate objective. It completely throws out TRPO's painful math and replaces it with a simple constraint. Think of it like putting bumpers on a bowling alley lane. If an action was good, PPO wants to make it more likely, but the clip flattens the gradient so it doesn't push the probability past a specific threshold, usually an epsilon of 0.2. And conversely, if an action was bad, it caps the gradient so you don't drop the probability below negative epsilon. It literally stops the model from becoming dangerously overconfident about a single lucky outcome, which guarantees stable, monotonic improvement.
When you zoom out and look at the whole picture, the entire architecture of PPO relies on the exact same actor-critic structure as older models, just with 3 specific components combined. First, you've got the clipped surrogate objective we just talked about. That's your main trick for stability. Second, the value loss, which trains the critic to predict future rewards using a standard mean-squared error. And finally, an entropy bonus, which basically gives the actor a little incentive to keep exploring new actions instead of getting stuck in a rut. This massive, industry-defining leap in AI capability essentially boils down to just one extra line of code wrapping the policy gradient. It's so elegantly simple.
Let's see how this actually runs in practice. Section 3, the PPO training loop.
Having the theory is great, but seeing the data flow is where the magic really happens. A standard PPO cycle runs in 5 steps. First off, collect your transitions across parallel environments. Second, compute your advantages and freeze them, treat them as constants. Third, and this right here is the absolute secret sauce, capture and freeze the old policy probabilities as a snapshot. Fourth,
Because we have our clipped surrogate bumpers in place, you can now safely run mini-batch updates for K epochs, usually about 10, on that exact same data. Only after those 10 epochs do you finally move to step 5, toss the rollout and repeat. Sample efficiency goes through the roof, and your policy stays completely intact. Think of this as your pilot's pre-flight diagnostic checklist. You need to watch 3 things every single update to make sure your training loop is actually healthy. First, mean KL divergence. This measures how much your policy is changing. It should stay between 0 and 0.02. If it blows past 0.1, you are drifting way too fast. You've got to reduce your epochs or your learning rate. Second, your clip fraction. How often your clipping actually triggers. You want this around 0.1 to 0.3. Near 0, your model is being way too timid. Over 0.5, you're overfitting. And finally, explained variance, which tells you how well your model predicts its real reward. That should be steadily climbing toward 1.
Even with all this legendary stability, things absolutely can go wrong. Section 4, Common Pitfalls.
The tricky thing about PPO is that it often fails silently rather than crashing your program. Here are the quickest ways to break it. First, tweaking that clip coefficient away from the standard 0.2 is a bad idea. It just invites instability. Pushing your epochs past 20, that'll cause dangerous policy drift. Skipping per batch normalization for your rewards and advantages will absolutely wreck you on most benchmarks. And keeping a constant learning rate is generally a mistake. A linear decay to 0 performs way better. But seriously, pay special attention to this last one, the gradient sign. Maximizing the surrogate objective means you have to minimize the negative clipped loss. A flip sign right there is the single most common bug in custom PPO code bases, and it will quietly ruin your model without throwing a single error.
Also, if you're writing this out in Python, this specific code-level optimization is absolutely critical. Calculating your importance ratio by just dividing the new probabilities by the old ones? Don't do it. It leads to catastrophic numerical instability because of floating point errors. Instead, use the exponential of the difference in logs to maintain your mathematical precision. Trust me, the research shows this isn't just some algorithmic folklore. It's a load-bearing trick that will literally save you weeks of pulling your hair out.
All right, let's wrap this up. Section 5, PPO in the real world. So why does PPO's legacy still matter so much today? Because its footprint is quite literally everywhere. Continuous robotics control in Mujoko, we use PPO with a Gaussian policy. Discrete games like Atari or massive agents like OpenAI 5, PPO with categorical policies. But here's the real kicker. That exact same PPO loss shape, the clipped surrogate plus value and entropy, is the foundational scaffolding for aligning today's large language models. Through RLHF, reinforcement learning from human feedback, PPO is exactly what teaches chatbots to actually be helpful. It's even the direct ancestor of GRPO, the variant powering the absolute latest reasoning LLMs today.
Ultimately, PPO didn't replace A to C and TRPO because it calculates some flawless, mathematically perfect gradient. No, it replaced them because it trades perfection for extreme, highly efficient practicality. You can get a hyperparameter wrong by 50%, and PPO is probably still going to converge and train a highly competent agent. Its true superpower is just being relentlessly robust. It saves engineers countless hours of tuning. That realization that being good enough practically always beats being theoretically flawless but impossible to run is the absolute hallmark of modern AI engineering.
I want to leave you with a bit of a challenging thought experiment. The original paper actually proposed an alternative to clipping. They suggested an adaptive KL penalty, where the penalty doubles or halves based on the observed divergence. Now, the clipping version won out because of its sheer simplicity, but that KL variant actually survives today in RLHF. So ask yourself, if you swapped the hard clip for an adaptive penalty in a standard environment today, how would it change your model stability? Exploring that question is going to test your true understanding of how this AI revolution was built. Thanks for joining this explainer. Keep questioning and keep exploring.